Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 6. In this lecture, we'll discuss damped oscillations. This topic is covered in Chapter 15, our textbook by Surway and Jewett. So far in our study of oscillating systems, we've considered two important examples, the mass spring system and the pendulum. You may have noticed that in both of those cases, we ignored the effects of friction or air resistance. In effect, we assumed that the energy of the system is conserved, and therefore the system is going to continue to oscillate forever and ever. That's not a very realistic assumption. A real mass spring system eventually stops oscillating. That's because a real mass spring system loses energy because of friction or air resistance or other factors. In general, any force that reduces the energy of an oscillating system is referred to as a damping force. In this lecture, we want to understand what the effect of damping forces is on oscillating systems. In this lecture, we want to understand what happens to the motion of a mass spring system as it loses energy with each oscillation. In general, many factors contribute to damping. So friction could be one example of a damping force. Air resistance is another damping force. Strain can also dampen oscillations. As a mass spring system oscillates, the spring is stretched and compressed. That deformation of the spring, that changing of the shape of the material of the spring, is referred to as strain. It turns out this strain can actually heat up the spring and therefore convert the kinetic energy of a mass to thermal energy. So this is yet another factor that could contribute to the damping of an oscillation. It turns out there are many reasons why an oscillation could be damped. An effective model for all of these damping forces is to view them as a resistive force. You might recall from your mechanics course or from Chapter 6 of our textbook that a resistive force is any force that resists the motion of an object. A resistive force is any force that basically slows down an object. So air resistance or drag is an example of a resistive force. The viscous force that an object encounters as it moves through water or a liquid is also a resistive force. For us, in this class, we'll adopt a relatively simple model. Any force that dampens an oscillation will be modeled using this equation. So we'll use the letter R for resistive force, and we will assume that this resistive force is going to be equal to minus BV. V is the velocity of the object. B is referred to as the damping coefficient. If there's a lot of friction, if there's a lot of air resistance, then B is going to be a large number. If there is almost no friction, because the mass spring system, for example, is oscillating on a lubricated table, or because the pendulum, for example, is swinging inside a vacuum chamber, then we can say that there is almost no damping. In that case, B would be a very small number. The minus sign is telling us that this resistive force points in the opposite direction to the velocity. So if the object is moving to the right, the resistive force will point to the left to slow it down. If the object is moving downwards, then the resistive force will point upwards, again, to slow it down. So now we want to know what the effect of this resistive force is on a mass spring system. To answer that question, we need an equation of motion. We basically need a differential equation that we can then solve to find out how the position, velocity, and acceleration of this mass spring system is affected by this loss of energy. As usual, we'll begin with Newton's second law of motion. The net force is equal to mass times acceleration. In this case, we have two forces in the x direction. I am assuming that the mass spring system is a horizontal mass spring system. So all motion is in the x direction. So we need to consider the x component of the spring force, and we need to consider the x component of the resistive force. These two components can be negative. The sum of these two forces must equal to mass times acceleration in the x direction. According to Hooke's law, the spring force in the x direction is simply minus kx, and the x component of the resistive force is minus b vx. That comes from this equation here. All of that must equal to mass times acceleration, and I'm expressing the acceleration as the second derivative of position with respect to time. I can now rearrange this equation a little bit to isolate the second derivative on the left side, and I finally arrive at the equation of motion. This equation is known as the damped mass spring differential equation to distinguish it from the simple mass spring differential equation, which we saw in previous lectures. This equation tells us that the position of a damped mass spring system is described by a function x of t, and when you take the second derivative of that function, you basically get the first derivative times some constant plus the function itself times some constant. Our goal now is to find a solution to this differential equation so that we can finally understand how the mass spring system will oscillate in response to this damping force. Solving the damped mass spring differential equation is somewhat challenging. To systematically solve that equation and arrive at a solution, you really need to take an entire course on differential equations, which I encourage you to do in the near future. For us in this class, the procedure that is used to find the solution isn't so important. What is important is the final solution itself. The solution to the damped mass spring system is this complicated function here. I don't expect you to know how we arrived at this equation. However, I do want you to understand how to use this equation and how to interpret it. According to this equation, the behavior, or more precisely, the position of a damped mass spring system is given by the product of some constant times an exponential function times a trigonometric function. This function could be a sine function as well. However, we often use the cosine by convention. Notice E here is the Euler number, and in the exponent is this entire quantity, minus b over 2m times t. So we have an exponential function here that is being multiplied by a trigonometric function. If you took this entire function and plugged it into the damped mass spring differential equation, you would find that omega has to equal to the square root of k over m minus 1/4 b squared over m squared. So if you know the spring constant and you know the mass and you know the amount of damping, the damping coefficient, then you can calculate omega. There is no simple formula for A and phi. To figure out A and phi, as usual, we need to know what the initial conditions are. So we need two additional pieces of information to figure out these two parameters. We need to know what the initial position and the initial velocity of the damped mass spring system were. Using that information, we can calculate A and phi. If you were to make a graph of this function, this is what you would see. On this graph, t is on the horizontal axis and the x-coordinate is on the vertical axis. This graph hopefully is not too surprising. As you can see, the displacements of the mass spring system are gradually decreasing in size, indicating that the oscillation is gradually dying out. The cosine function is responsible for the oscillatory periodic behavior that you see, and the negative exponential is responsible for this decrease in displacement. Hopefully you remember what a negative exponential looks like. From your math classes, you should remember that this is what e to the minus t looks like. A positive exponential rises quite rapidly, and negative exponential decays or falls quite rapidly. This decaying behavior of the negative exponential is what's responsible for the decrease in the amplitude or the maximum displacement of the mass spring system. To better understand the behavior of the damped mass spring system, it's helpful to see its behavior compared with the simple mass spring system. So on the right-hand side here, we have an undamped oscillator, like the simple mass spring system. And on the left, we have what we've been talking about, which is a damped mass spring system. When there is no damping, the position can be described as a simple function, a simple trigonometric function. It could be a sine or a cosine. We usually choose the cosine function. A is a constant, it's often known as the amplitude. Phi is also constant, it's often known as the phase constant. And the angular frequency omega is simply the square root of k over m. This quantity is often referred to as the natural angular frequency of the mass spring system. The situation becomes a little more complicated when damping is introduced. Again, we have the cosine function describing the position, but in addition to the cosine function, we have an exponential function. So we have a parameter a that is multiplied by an exponential function, and that entire thing is multiplied by the cosine function. A is referred to as the amplitude. However, you should be careful because sometimes people refer to this entire quantity, a times the exponential function, as the amplitude of the damped oscillator. So pay attention to the context, and usually you can discern whether they mean just a or a and the exponential function included. Omega in this case is a more complicated function of the spring constant, the mass, and the damping coefficient. This quantity here is referred to as the damped angular frequency of the mass spring system. Notice that if we set b equal to 0, all of the equations on the left side reduce to the equations on the right side. For example, if we set this b equal to 0, then we'll end up with e to the 0, which is just 1, so the position can be described as a cosine of omega t plus phi. Similarly, under this square root symbol, if we set the b equal to 0, then we get square root of k over m, which is exactly what the natural angular frequency was. So you can think of all of these equations on the right side as a special case of the equations on the left side. So let's finish this lecture with a practice problem. A damped mass spring system is described by the following parameters. Its mass is 2 kilograms, its spring constant is 300 newtons per meter, and the damping coefficient is 5 kilograms per second. How long does it take to complete 5 oscillations? So we have a damped mass spring system, which means its oscillations are going to decay, or they're going to gradually die out. It will manage to complete at least 5 oscillations, and we want to know how long that takes. We want to know the period of time in seconds that is required to complete 5 oscillations. To answer this question, it helps to think a little bit about how a damped mass spring system oscillates. The position is described by this function here, where we have a constant coefficient times an exponential function times a trigonometric function. You have a periodic behavior that is decaying in amplitude. We're interested in basically knowing the amount of time that is required to go from, let's say, its starting point to 5 oscillations later. So this would be 1 oscillation, 2, 3, 4, and 5. Now, don't take this graph too seriously. These numerical values don't necessarily apply to this particular problem. The problem doesn't really specify, for example, what the initial position of the mass spring system is. It turns out it's not important for what we want to do, but this graph is supposed to be just an example. The important thing here is that the period of time from one oscillation to the next is known as the period. It's denoted by capital T, and as we learned a couple of lectures ago, the period is equal to 2 pi over omega. So if we can figure out the angular frequency of these oscillations, then we can figure out the period. The period tells us how long it takes in seconds to complete one oscillation. Once we know how long it takes to complete one oscillation, then we can calculate how long it takes to complete 5 oscillations. It turns out that the period of the oscillations is constant. So although the amplitude is decaying, the amount of time required to complete one oscillation does not change. So how do we calculate the angular frequency? Well, we have a formula for the angular frequency. This is the formula. We know what K is, we know what M is, we know what B is. At this point, you can plug those numbers into your calculator and you will find that omega is 12.183 radians per second. Now you can calculate the period, and once you know the period, you can calculate the amount of time for 5 oscillations. The amount of time, delta t, is equal to 5 times t, so remember capital T is the period, and the period is 2 pi over omega. We can now calculate that, and we find that the period, the amount of time required for one oscillation, is 0.516 seconds. Multiply that by 5, and you will find that it takes 2.579 seconds to complete 5 oscillations. And that is the end of this lecture. Thank you for your attention.